Sorry, Papa Francis. It's 11:43. So, introduction to control. So this is like a whole cool topic. I'll kind of go through this, and then we're going to talk a lot more about it. So control theory is the study of control systems. Systems that control the behavior of other systems, okay? It's sort of a strange definition, but it's kind of the best one, I think. This means that control theory is fundamentally about design as opposed to the analysis of many engineering topics, including system dynamics. So system dynamics, dynamic systems, what we've been discussing the whole term, that's been all analysis, right? We've been analyzing systems. I mean, there's some opportunity for some design in there, and it's an indispensable design tool, but it's been focused on analysis. And now when we do control, we're saying, okay, we want this thing to behave in a certain way. This is design, okay? Okay. In control theory, a system, usually called the plant for historical purposes, is analyzed, often with system dynamics. Then a control system is designed to control the plant. So we have a plant or a system that we want to control, okay? And so we analyze it first, and then we design a control system to match that plant to make it behave the way we want, okay? That's the idea. A control system usually controls the plant by changing one or more of the plant's inputs. The plant's outputs are variables we would like to know and or control. Okay? So some of the outputs might be measurements that we make that make us help us to understand the system better. And oftentimes we're going to use those to feed back and affect what inputs we give to the plant to make the outputs behave the way we want. Sometimes the output is something we want to control directly, like maybe it's like the fluid level in a tank or something. And that's what we want to know directly. We want to control that variable. Other times the variable is just of interest to us, but not something that we want to control directly. So there is a slight difference, but if a plant is mathematically modeled with sufficient accuracy, a controller can specify the plant's input, which is the controller output, right? So the controller outputs into the plant. If we can mathematically model the plant with sufficient accuracy, a controller can specify the plant's input to produce the desired output, right? If we know the plant perfectly, we can just say, oh, well then if I put in this input, I know I'm going to get this output. Okay? So if you know it perfectly, then that's all you need to do, right? This is called open loop control. However, most plant models are not understood well enough to do this. It is especially difficult to model outside disturbances like sudden jolts from being bumped and environmental interference. So these are things that are hard to have control of in your process. So an example would be if you're going to control, say, the speed of a motor based on the voltage you apply to the motor. Say you model the thing and you're like, okay, I know if I put this voltage in, it'll be about at that speed. You can do okay with that, but if things change slightly in the environment, or parts wear a little bit, or different things happen in your electronic system, or like maybe the model doesn't take into account something about like the resistor heating up and changing how much dissipation you get in your motor, then you're going to be inaccurate. And almost any sort of disturbance that happens, like if something happens to somebody's like, oh, okay, well, this is on a conveyor belt that's been, moving this load on it. We're going to double that load. That changes the whole thing, right? And no longer is that voltage that you apply to the motor going to result in the speed that you wanted. So if it's open loop, you have to know that system perfectly to make that output what you want. So it's tough to do open loop. For this reason, most control systems include feedback, which is measurements of the plant's outputs. So we measure like what's the actual speed that the motor is going at, or what's the actual speed that the conveyor belt's going at. These measurements are fed back to the controller, which determines its output. Remember, that's the plant's input from this information. Determining how the controller should respond to the feedback to control the plant's output is the subject of much of control theory. So how to make decisions when you have some measurement, say like it's going at 3 meters per second right now, the goal is to be going at 3.2 meters per second. What do you do? Like how do you change what your input is, say your voltage to the motor? What do you do? What's the decision that you make as a controller? So this is what control theory is all about. And actually, in my mind, why I think it's so cool is that this is the beginning of our thinking about making artificially intelligent things. Okay, this is the foundation of that whole computers, AI stuff. All starts with control theory. It's saying, how do you make a machine do something intelligently? Okay, so you want this to happen. How do you monitor what's happening, and then tell well, not tell, but command that from the machine in a way that's effective. So there are several types of controllers used in control theory. Which is best for a given system is the primary task of the control engineer. There are design trade-offs to be made. Some controllers will be more expensive to implement than others because they will require more expensive hardware. Some controllers will perform better than others in some aspects we will now explore. So performance is the first thing that we'll discuss. How do we determine what the performance is of a controller? So we'll pick that up on Wednesday. Yeah.